Informally, all it needs to be a field is plus, minus, multiply, and divide all walk the way that you think they should. Approximately the way that you think they should. But you can do more than add, subtract, multiply, and divide real numbers. You can also ask, is this real number bigger than that real number? There's that notion of inequality. That's what we're going to do. And the way that we'll do it is we won't directly specify a sense of order. Instead, we'll specify what it means for a real number to be positive. Because if you know what it means for a number to be positive, how can you tell if x is bigger than y? If you know only what it means to be positive. It's a bigger number, it's bigger, but you just use the word bigger to define bigger. So, but that's kind of the point of what we're doing. You have to build up some things with axioms. So what I'll specify is a set of positive numbers because if you can specify the positive numbers, you can say that. X is bigger than y if the difference is positive. So that's the approach we'll take. And let's go ahead and get started. Let's specify the properties of the positive numbers. So, definition. An ordered field, F, is a field together with a non-empty subset, P, the set of positive numbers. It's important that the set of positive numbers not be empty. And that makes sense, right? There should be at least one positive number, which should satisfy some properties. P should be closed under addition. If A and B are positive numbers, then what do you think I'm going to claim? Yeah, and that should be true, right? I take two positive things, I add them together, I should still get a positive thing. And these are just axioms. P is closed under multiplication. If A and B are positive numbers, then what should also be positive? Good. The trichotomy law. The trichotomy law says that there are three types of numbers for each field element A. Exactly one of the following holds. I'll give you one of the options for free. A is a positive number. So there are three types of numbers. There are positive numbers. There are negative numbers. And there's, what's the last type of number? Zero. Zero. So the three options, as you said, are A is positive. That's what this option is. A is negative. Or A equals 0. A equals 0 is easy to write. That's just A is equal to 0. If you only know what it means to be positive, how can you say what it means to be negative? It should mean that like negative it is positive. That's the same as being negative. The reason negative 5 is negative is because negative 5 is positive. And those are the axioms. So the second axiom of the real numbers is that the real numbers form an ordered field. And so let's just explore ordered fields today. So you'll notice that nowhere here did I specify that any particular number is positive. What is a number? What is an element of a field which you think ought to be positive? Should 1 be positive, negative, or equal to 0?
Positive.
Should probably be positive. It better be. If 1 is negative, then we probably just need more axioms to eliminate that possibility. Let's prove that. Let's prove that 1 is positive. Let F be an ordered field, and 1 be the multiplicative identity of F. Then 1 is in P. Let's try to do it. So for the sake of contradiction, let's suppose that 1 is not in P. We'll negate what we want to prove. If, by the trichotomy law, if 1 is not in P, then one of two other things must happen. What are they?
It's either equal to 0 or negative.
It's either equal to 0 or it's negative. Oh, I guess those are written. Either 1 is equal to 0 or 1 is negative. I guess those are the opposite order of B and C, but they're numbered 1 and 2, so that's okay. I know for a fact that P is non-empty. That's one of the axioms. That's one of the assumptions given up here. So I will let P be in P. I will let P be a positive number. So let's just go through one case at a time. In the case that 1 is equal to 0, I don't want to look at my previous notes. Let's just look through this. So P should always be the same as 1 times P. But if 1 is equal to 0, what is 1 times P the same as? Same as 0 times P. And what's 0 times P the same as? Does this contradict the trichotomy law? Yeah.
Yes, it does, because it says for each A and F, exactly one of the polynomials, not more than one.
Yeah, only one of them can be true. Which two do we have true right now?
And A is positive and A is 0.
Yeah. So this contradicts the trichotomy law, because right now I have both P, little p, is in big P, and little p is equal to 0. Cool. And we could look up exactly what the error was that I'm using there, but I don't want to take the time. In case 2, let's suppose that negative 1 is in the set of positive numbers. In this case, let's see. How could you represent negative p in terms of multiplication? Negative 1 times p. Was that one of the homeworks, or did we do that in class? Homework? We did it in class? Okay. Either way, we know it's true. Yeah. It was stated as a corollary in class, but then you proved it in homework?
We did? Yeah.
Okay. Awesome. Negative p is the same thing as negative 1 times p. Wait, I spelled out the contradiction. What did I assume about negative 1? It's in P. What did I assume about P? That it's also in big P. So what do I conclude about negative 1 times P? I'm going to get a contradiction out of the trichotomy law, because I'll get negative P is in the set big P. So this contradicts the trichotomy law because negative P is in P, and P is in P. That makes sense? How do people feel about that? Cool. So here is the axiom of the day. The real numbers form an ordered field, and this might seem slightly counterintuitive. Instead of specifying an ordering, I've specified what it means to be positive, but if we know what it means to be positive, then we know what it means to be bigger than. Definition. Let F be an ordered field. Let's let P be its set of positive numbers. That's what it means to be an ordered field. The ordered field knows what the set of positive numbers is. If A and B are in F, then I'll say that A is bigger than B if B minus A is positive. I'll say A is bigger than B if A minus B is positive. I'll say A is bigger than or equal to B if, well, how about this? If A is less than B or A equals B. I'll say A is bigger than or equal to B if A is bigger than B or A equals B. People feel pretty okay about those just as definitions? Nice. So here is, I don't think it's posted right now, but a challenge problem that will be posted under today, even if I don't get it posted today. We'll say that there's another track to understanding an ordering. You could just put a bunch of axioms on what this symbol should do. And those axioms we'll prove right now as a theorem. Let's let F be an ordered field and A, B, and C be in F. Inequality should be additive. If A is bigger than C, then how should A plus C and B plus C compare?
A plus C should be less than B plus C.
Yeah, you should be able to add a number to both sides of an inequality. If A is less than B and B is less than C, then A is less than C. If A is less than B and C is bigger than 0, so notice, let's just expand that out. 0 is less than C. What does that mean? That means C minus 0 is in the set of positive numbers, i.e. C is in the set of positive numbers. Okay, so the set of positive numbers is the set of numbers bigger than 0. That's nice. If I take A less than B, and let C be a positive number, then what happens to an inequality when I multiply it by that positive number? It is resolved. Same thing, but what if C is negative? If A is less than B and C is negative, then which is bigger, A times C or B times C? And this last one doesn't need to be an axiom, but I think it's a good result anyway. If I take any number that's not 0, I'll set A squared to be A times A. What can you tell me about A squared? How does it compare with 0? Greater than 0. So, if anything, that example is telling you what I'll mean by colon equals. That will tell you that I'm defining something by this. A with a little 2 in the superscript means A squared is A times A, which you already knew, right? But one should actually say what notation means when one introduces it. So let's prove some number of these. I'll start with the first one. So let's consider any A, B, and C in F. I want to prove this claim. So if I want to prove that implication, what should I assume? A is less than B. According to the definition of inequality, what does that mean? Yeah, but I'll say it in terms of the positives. And now let's think about what we want to show. So let's sketch our argument here. So right now we are given B minus A is in P. We want A plus C is less than B plus. And so let's just trace these out. What does that mean?
That A is less than B.
Yeah, so we're trying to prove the converse of that. So we want to prove that we can do arithmetic to an inequality. So we better not assume that we can. Let's use the definition. This symbol means B plus C minus A plus C is in the set of positives. And since last time we dealt with the elementary arithmetic in algebra all walk, so we want to go from here to there. And we can come at it from either side. What would you want to do to make either one of those look more like the other one? Yeah.
Can I add 2c to b minus a, because it'll still be in the positives.
Do I know that C is positive? So instead of that, let's actually figure out what we really need to do by distributing the minus sign, which I guess we didn't really justify last time, but we could, and so I won't. Right? Negative a plus c, we've proven that's negative 1 times a plus c. Now we can distribute. Aha. So do you want to add 2c to both sides? No, it turns out you don't, right? Why should these two be the same?
Because c minus c is just 0.
Cool. So I think this gives us a plan. And what gives us more than a plan, it gives us the proof. Now we just need to put WADs to it. So we know that b minus a is in P. We can add 0, because 0 doesn't change anything. So, because c minus c equals 0, I see that b minus a plus c minus c is in big P. That gets us there. How do we get from here to there? By commutativity, b minus b plus c minus a minus c is in big P. How do I get from there to there? By the distributive properties. By distributive law.
Would you be able to move it up just?
Oh, yeah.
Thank you.
Thank you. Distributive law. Maybe it's even the distributive law. B plus C minus A plus C is in P. All right. And so, what can we conclude? Exactly what we want, I hope. So, by the definition of inequality, B plus C is greater than A plus C, as we claimed. That feel pretty okay? And I guess the next line without blanks is actually the concluding sentence again. So. So I'll give you guys a choice now about, well, no, I think I'm not going to give you the choice. Think about the second one, the proof of transitivity. So let's suppose A, B, and C are an F. Let's assume that A is less than B, and B is less than C. I want you to show that that means that A is less than C. And well, so what do you guys think? Do you guys think you're able to get started on that without me saying anything? And you don't want me to say some starting words? Awesome.
Quick question, Dr. Davis.
Yeah.
What's definition 1.4.4?
Well, hopefully it is that's problematic.
I think it means 1.2.
Yeah, all do. Okay, so the reason that happened is a technical issue a law technical error that I made while preparing these notes.
That's fine, I just wanted to clarify,
Yeah,
it should
yeah.
be 1.2.3 then?
Yep.
Okay.
That doesn't same in the other, consider any A, B, C, and F, assume that, yeah, that was.
Okay. You guys can like talk to each other if you want. Based on the volume level in the classroom before I start talking, like, you guys don't mind talking to each other.
So we know that they're both.
C must be, yes, could you do?
So since they're both positive, I have to compare those somehow. I can just answer the questions.
Yeah.
A minus C. That's right. Yep, so we don't know how those compare though.
Cool. So I mean, what sounded like some pretty good summaries of what the proof is. Let's talk through the proof. So let's suppose that A is less than B and B is less than C. What does that mean?
B minus A is in P, and C minus B is in P.
Cool. And I want to get that A is less than C eventually. So what should I do?
Can you, because you know they're both positive, can you put them, like add them together to get there?
Yeah. So by the closure of P under addition, B minus A plus C minus B is in P. Okay.
Can we pull up the common B?
Yeah, maybe I'll see by maybe the distributive, well, not distributive, because there's no multiplication. By associativity / commutativity. Because associativity means that you can always parentheses, right? Basically. And I want to get rid of those parentheses. I see that C minus A plus B minus B is in P. So, what can I conclude because of that?
C minus A is in P.
So what can I conclude because of that? So does that mean we're done? Yeah, that's exactly what we claimed. The other results all have fairly similar proofs. I mean, you guys couldn't see what I was writing, but you guys had already written it anyway. Write a concluding sentence. Cool. And in fact, the concluding sentence is like right there. So, the other two results really have similar proofs. So I think I might even just want to say, I'm not going to, do people want me to prove the remaining result that the nodes have a proof, space for a proof of? Okay, then I will do. So let's prove the third result. Let's prove that if A is less than B and 0 is less than C, then AC is less than BC. So let's let A, B, and C be in F. Let's assume that A is less than B and 0 is less than C. All right, let's do it. So what do we get to, by the definition, but the correctly numbered one, what does that mean we get to assume? What do we get to conclude because of those assumptions? How can we translate this to something about positive numbers?
B minus A is in B.
And?
C minus 0 is in B.
Yeah, but who cares about minus 0? So those are the things that I know. Maybe off to the side, what is it that we want to prove? What is the thing that we want to show?
B times C is less than B times C.
So what is the translation of that into this subset P? All right, so there's what we have now. I know that. I know that. How can you get that? Yeah.
Since it's closed under multiplication, you can multiply B minus A times C.
Yeah, so by closure of P under multiplication, I see that B minus A parentheses parentheses times C is in P. Awesome. Good. What next? By the distributive law. Guess that's BC minus AC is in P. Okay.
And then we can conclude that AC is less than BC.
Nice. That seemed pretty okay. The remaining one, where there's this condition that maybe C is negative instead, is going to be basically the same. You'll just have to remember that there will be a negative that'll show up, I guess. Cool. So, the next thing that I have in these notes is something which we'll solve as a quick review of induction. So let's just see a show of hands. If I say mathematical induction, how many people know it, have heard that string of words before at least? Every hand should be up. Good. How many people feel happy about mathematical induction? Okay. Good.
Is that the domino theory when one's true? Okay, yeah.
Yeah.
Good.
Yeah, let's prove some statements. So we are going to prove these. Let's let x be an f and n be a natural number. If x is bigger than 1, then how should 1 compare with x to the n? Oh, yeah. Thank you. Let n be a natural number, let x be an element of f. If I raise x to the power n, how should that compare with 1?
Or it should be greater than 1.
Yeah. Unless x is between, x is between 0 and 1, then what? And what if x is exactly equal to 1?
It's just 1.
It should be the same as 1. Now, you'll notice that I stated that beyond, but I didn't actually go through the definition of what x to the n means. Here is a recursive definition of x to the power n. How do people feel about recursion? Presumably exactly as good as they feel about induction? Because they're like one of them's good to it and the other one's equal to it, I guess. Let f be a field, let x be an n. For any natural number n, I will define x to the n recursively by the rule that x to the power 1 is x. And for any natural number n bigger than 1, x to the n x to the n is the same thing as x times x to the power n minus 1. Right? People are happy with that? And I don't want to say that x to the n means x times x times x times x n times, because in order to make sense of what it means to write down x n times in a row, you're going to basically need recursion anyway. So, there's the definition of what x to the n means. Let's prove these. Since we're proving something about a recursive formula, I guarantee that there will be a proof technique that uses induction. Let us prove. And let's do like the easiest one first. Let's prove that if x is equal to 1, then x to the n is equal to 1 for every n. Just for a nice induction warm-up. Let f be an ordered field. Let x be equal to 1. So I'm proving claim 3. I need to show that 1 is equal to x to the n for every natural number n. The way that I'll do it is by induction. So let's prove this claim when n is equal to 1. When n is equal to 1, if n is equal to 1 and I want to show that x to the n is equal to 1, I just need to show that x to the 1 is equal to 1. So tell me, why should x to the 1 be equal to 1?
Because x is 1 and what the 1 is equal to 1.
Yeah, great. Maybe I'll say those words in the exact opposite order, though. By the definition of exponentiation, x to the 1 is equal to x. But what did I assume about x? That it's equal to 1. So those are the same steps as you said. I just said them in the opposite order. And so we get the desired result. People feel pretty okay? All right, and as per usual, when you're proving something inductively, oftentimes the base case will be the easiest one to prove. That's not always true, but oftentimes it is. All right. And remember, I'm still assuming that x is equal to 1. Inductive step. Let's consider any natural number n. What do I get to assume about x to the n?
That's going to be greater than 1.
Well, equal to 1 in this case, right?
Oh, equal to 1.
Yeah, I'm doing the case 3, which is like the stupid case. What do I need to show about x to the power n plus 1? Very good. All right, so let's try to do that. So tell me about x to the power n plus 1.
It's x to the n plus x to the 1.
Not quite.
Times x to the
Yeah, that one.
All right. By the definition of exponentiation. Good. What next?
Yeah. But
That equals 1 times x to the 1 by our assumption.
Yeah, 1 times x to 1. I'm going to add a word to what you said by the inductive assumption. Cool. What next?
And then by our base case, we know that it's equal to 1 times 1, which is 1.
All right, and 1 times 1 is equal to 1, because 1 is the multiplicative identity. That seem pretty okay? How do people feel about induction? Pretty all right? Okay. Let's do, yeah, this is like the last thing. So let's prove the next one. Let's prove the claim when x is bigger than 1. So let's let f be an ordered field, and let us suppose that x is bigger than 1. We want to show for all n in n, x to the n is bigger than 1. Cool. So let's do it. Base case, n is equal to 1. What do I need to show in the base case? Why is that true?
Because of our assumption.
Yeah. Like, proofs need WODs, so there should be WODs next to that, but I think you know what the WODs should be. Do people want me to write WODs? Okay, very good. Inductive step. Consider any natural number, n, in Blackboard hold n. Are people okay with me using that for the natural numbers? Okay, I'm going to continue doing that, so now you are okay with it. Consider any n in the natural numbers. What should I assume?
That x to the n is greater than 1.
What do I want to show?
That x to the n plus 1 is greater than 1.
Cool. So let's do. How should this work? Maybe I'll just let you guys like do it, and then you'll tell me how you did it. Apparently also need to be reminded frequently that you can like talk to each other on the same thing. There's like a midterm and a final exam, and you won't be able to talk to each other then.
By the inductive assumption, we know x to the n is greater than 1, but the base case we know that x to the n is greater than this. So I'm just to include wherever multiplication. Is it possible?
Yeah, so
Yeah.
Can you, like, I'm not write it down, but so you can tell it's like 1 times the why the first one is because it is the base case, so it's not justified by the base case, but it It's like the last one, is the definition of exponentiation.
Yeah, this is by the because x to the 1 is by definition
Okay.
x. So, tell me about x to the power n plus 1.
Same thing that we did in the last one.
Same thing that we did in the last one, but let's be more specific. What's the first step that we did in the last one?
That's equal to x to the n times x to the 1.
And what else did we do in the last one?
We used our inductive assumption.
We used our inductive assumption, so maybe I'll just write that down. By inductive assumption, okay.
We can say x to the n times x to the first is greater than x to the n by the definition of inequality. Oh no, it's greater than x to the n.
I wouldn't say that's by the definition of inequality. Instead, I think what I would say is so tell me, which is bigger, x to the 1 or 1?
X to the 1.
Is x to the n positive? So is this just multiplying a known inequality by a positive number? Have we proven that that's correct? So let's just parse that out. No, you could do this in different orders. So it looks like it's important that x to the 1 is bigger than 1, and x to the n is bigger than 0. So by assumption, x to the 1 is bigger than 1, and x to the n is bigger than 1, which in turn is bigger than 0. Yeah.
Your first sign shouldn't be equals, right?
This one?
Yeah.
It should be equals, but it should be correct and not incorrect. So as x to the n is bigger than 0, I can appeal to the fact that when you multiply an inequality by a positive number, it resolves the inequality. Let's cite that. Theorem 1.2.4, item 3. So by theorem 1.2.4, item 3, I get x to the n times x to the 1 is bigger than 1 times x to the 1, which is equal to x, which is bigger than 1. Does this now prove that x to the n plus 1 is bigger than 1? Yeah. So, as x to the n plus 1 is equal to x to the n times 1, x to the n plus 1 is bigger than 1. X to the 1. Well, you couldn't read it anyway because it was so small, but I did write down something incorrect. People feel pretty okay about that proof, the way it went? Cool. So, there are like 4 minutes left, and I did actually prepare these notes with the intent of finishing with just a few minutes to spare. There's some homework on the next page. Yeah. There's homework on the next page. which, if you like, you can take these 12 minutes to make a start on. Yeah.
My brain didn't understand what snaps was. I don't know. Right?
That'll be useful. And also,
I have your phone number, but I don't know.
Yeah, because right now, 5 plus 0
I'll take it.
is
I'll take it.
Yeah, right. Every rational number is a real number. Every real number.
Other weekend, yeah, that was.